In the previous lesson, we looked at the exchange between gravitational potential energy and kinetic. Gravitational is a type of stored potential energy. Today, we're going to look at a different type of stored potential energy, elastic. Now, elastic potential energy is energy that's stored in materials that stretch or compress. This is a spring, and as you can see, when you squeeze it, you transfer gravitational energy to kinetic, pushing down, and that kinetic energy then is stored in the spring, so that when you take your hand away, it moves using that stored energy. Stored energy usually transfers into kinetic. Here we can see another example of a transfer of energy from stored to kinetic. Initially, this running athlete, so you can see here you've got kinetic energy, is then transferred to the elastic energy of the pole, which then is transferred to gravitational and then to kinetic again. Now let's look at the main features of a spring, for example. Now, before we can look at the energy in a spring, we are going to review the main properties of springs themselves. Springs are usually described, or their behavior under loading, when you squeeze them or pull them, their behavior depends on something called a force constant or spring constant. That constant is called K, and we can find the value of that K by plotting a graph of force against extension, or in this case it would be compression. Force extension graphs for springs are straight line graphs, and the gradient, the slope of a force extension graph for a spring will give you the force constant, or the spring constant K. The area would be equivalent to the work done. If you remember, going back to our introduction of work done, we said that a force distance graph, if you have a force distance graph, you can work out the work done from the area underneath it. This is no exception. If we have a force extension graph for a spring, the work done is the area under the graph. Let's have a look at the equations. The spring constant K is equal to force over extension, and it's best worked out as a slope. The elastic potential energy, the energy stored, is equal to the area under the graph. The final equation that we get, is a half kx squared. Let's have a look at how you can derive this expression. The area under this graph is a half force times extension divided by 2. So here we can see the stored energy would be equal to a half force times the change in extension. However, we know from this equation that the force is equal to kx, or change in x. If we substitute this into here, we're left with a half kx times x to give us our final expression for elastic potential or strain energy, same thing, equal to a half k change in x squared. And that's our final expression. Now, when you go on to grade 12 maths, you will see these two ideas as differentiation, which gives us the slope, and integration, which is the area under. And so differentiation would give you your relationship for K, and integration will give you the area under the graph. You'll probably have no idea what I'm talking about at the moment, but this time next year you will, and you will hopefully remember these words. Now that we have these relationships, what are we going to do with them? Well, we're going to look at some energy changes. And the most common type of energy change is from elastic potential energy to kinetic, although gravitational potential can be introduced as well. Now, the idea of transferring elastic potential to kinetic energy would be applied to using a spring, squeezing a spring, and then letting go. Your mass, as you can see here, your mass here is pushing the spring. So what you're doing is you're bringing kinetic energy and you're moving this spring inwards. So that kinetic energy is being stored as strain. Okay, so that would be half mv squared equals half kx squared. And then here, once this spring is nice and squashed, it would, when you're releasing the mass, it will push that mass that way. So you end up having another transfer of energy from strain to kinetic. In that case, it would be a half kx squared equals a half mv squared. And by using these two equations, equating them, you can solve for an unknown. Have a go at some questions now. You can pretty much do all of these introductory questions and go on to the more complex questions like 101, 102, and 5. Have a go, check your answers, and then start working on the rather more extension questions, 18, 19, and 20.